Hello everyone, this is Project 1 for Dr. Arzvay's class, High Speed Aero. We are simulating a CD nozzle in Fluent, 2D simulation. And starting out, you want to get your geometry. And this is my basic nozzle geometry. I did this in SolidWorks. We're going to import it into Fluent. So just do whatever nozzle geometry you like, then save as a .step file. And then we're going to go into Workbench. Under Isentropic, right here with geometry, you add your nozzle. And let's go take a look at our mesh. While this loads, I'll go over the project. We need to get pressure, temperature, density, velocity, speed of sound, Mach number contours. And we also need to plot this above the center line. Then we'll do it. This is just for the isentropic one for this video. Okay. Now I did quadrilateral dominant mesh. I did 5e to -3 element size. And it's a pretty fine mesh. Looks pretty decent. Make sure to create your named sections, so inlet, your walls, and then your outlet. Yeah, that's basically all you do for mesh. Pretty easy. You can obviously refine your mesh further if you want, but let's go to setup and let's start this up. Wait for this to load. Alright, cool. Now, first thing you need to do, since this is compressible flow, you need to change it to density based right here. And then you go under models, make sure your energy is on, and you go to your flow type, make sure your model type, make sure it's inviscid. That about does it for that. Under fluids, your air, you need to make sure it's ideal gas, not constant. And then apply that. Let's go to boundary conditions. Alright. We need to change this to a pressure inlet and pressure outlet. You right click, go here, type, make it pressure inlet. Pretty simple stuff. And here, based on your nozzle, this is where you get your preliminary calculations going. My gauge pressure was 1E6 pascals and my total temperature was 400 Kelvin. I wrote these down here. Okay, that was based on my own calculation. And then our outlet, I did, for this isentropic flow, I did 101.32 kilopascals for my gauge pressure. Make sure to change it to static pressure. This should be your exit pressure. And your thermal, it stays the same, obviously, because isentropic flow, 400 Kelvin still. Alright. Make sure, under boundary conditions, go to operating conditions. You need to make sure everything's 0. Operating pressure is 0, gravity's on, all these zeros, operating temperature 0, operating density 0, and then you're good from there. Now, let's go to methods. I'm using second order, implicit, and my Crot number is 5 right now. That might change in the shockwave video. But anyways, come here and initialize. And then let's run our calculation. Now this may take a little bit, so just hold out with me. You can see the updated residuals right now. You want to get them as low as possible. Obviously, if you run more iterations, it will eventually converge, but you want to make sure it is as low as possible. It just drops significantly. That's good. So drop in about 450 more to go. And then we can get our plots and contours. Make sure for the graphs you make a center line based on how long yours was. Mine was 2 meters. Might make a 2 meter center line. I already did that, but I'll show you guys. Still have a bit more to go. You can always stop it preemptively. I'm just going to let it run to 1,000. But if you're doing this project and start getting huge residuals, you might just want to stop it and change your parameters. It's very useful. Don't always gotta let it run. Alright, there we go. Calculation's done. Now let's go get some contours. Under graphics, contours. Let's first do our pressure. Static pressure. Let's save and display. Let me get this here. Excuse me. You can see static pressure decreases across the nozzle. It's all standard theory. Should look like this. Temperature follows suit, and density should as well. Yes, that's right, density. And then let's see here. You get velocity, speed of sound, and Mach number. So let's do velocity. You really want to focus on X velocity, really. You see how that increases across the nozzle. And let's go to properties, speed of sound, or sound speed. Oh, that's specific heat, my bad. Sound speed. Got worried for a second. See, that's decreasing across the nozzle. And let's go back to velocity and get our Mach number. Right, so our max Mach number is 2.76. You see that the nozzle gets to 1, which it should. Alright, that does it for the contours. Let's go to plots, XY plot. And here's where you want to make a new surface, your line and rake. Mine was 2 meters. You can call it whatever you want. It's basically just center line. I already got the center line. And then let's do our pressures. See how it decreases? Should all look like this. Temperature, all suit, density, they all behave the same. And let's go to velocity. Should look different. Increases across the nozzle. Speed of sound. Under properties, decreases, and then Mach number increases. Mach number, velocity go with each other, and everything else does opposite. So that is part 1 of the project for the fully isentropic flow. Thank you for watching.